Hello, welcome to this learning module. In this video, we're going to learn about the overview of infrared spectroscopy. Just before we get started, I am recording at home today, so if you hear my kids in the background or other house noises, that's what that noise is. All right, so infrared is our second spectroscopic technique that we're learning. And let's remind ourselves what we know about spectroscopy. Spectroscopy is adding energy to molecules. The molecule absorbs some of that energy characteristically and responds, and we measure that response, and that tells us something about the molecule. So with IR, let's remind ourselves with IR, the IR looks at bonds. Remember, we can only get information about the question that we're asking. And mass spec looked at individual molecules, and IR is a little bit more specific. It looks at bonds. For infrared spectroscopy, the energy source is infrared light, so a little bit lower energy than visible light. And the way the molecule responds is certain bonds bend and stretch. They vibrate. The molecule turns that infrared radiation into kinetic energy, into heat, essentially. And what we measure which infrared wavelengths were absorbed. And again, because this is characteristic, if we see that there's an absorption at a certain wavelength, then that suggests that we have a certain functional group in the molecule. And so we can use that to start to figure out the structure of molecules where we don't know the structure already. So how does infrared work? In general, again, the broad overview. There is some kind of light bulb in one end of the instrument, and it is shooting out infrared light, all of the wavelengths of infrared light. Here in the middle, you have your sample, and the sample is placed in one of these salt plates. So these are two salt discs, usually potassium bromide, doesn't really matter, and in between them, you put a drop of your sample, and then you wedge them between two of these salt plates as a salt plate sandwich. And then you put it on a holding platform in the center of the IR, and that's where your sample sits. So the infrared light hits the sample, and some of that infrared light will not be absorbed by the molecule and will go through the molecule, but some of that infrared light will be absorbed by the molecule and therefore will not pass through the molecule. And on the other end of the infrared is some kind of detector that detects which wavelengths of infrared light hit it. So we have all the infrared light hitting the sample, but only some infrared light hitting the detector, and that difference is which wavelengths are absorbed. Now, it's more sophisticated than that, but that's a broad overview. Again, if you take an instrumental analysis course, you'll learn more about how all of these things work. And this is generally what an IR looks like. So let me orient you to what an IR looks like. First thing to say about an IR is the baseline for an IR is here at the top. That's a bit unusual. Typically we think about the baseline being at the bottom and the peaks extending up from the baseline at the bottom. Here it's reversed. The baseline is at the top and the peaks extend down from the baseline at the top. So when you're looking at an IR, that's the first thing to notice. The next thing is the x-axis. The x-axis is wave numbers, and it has the units of reciprocal centimeters, which is really odd. It just doesn't really make a lot of sense. But if you keep in mind that the way spectroscopy works is we're adding energy to molecules, and we want to know which energy values were absorbed. So when you take the wavelength of a molecule and you take its reciprocal inverse centimeters, that is proportional to energy. So the x-axis is a proxy for energy. Don't get too caught up in what the units are. That's not the most important part, but that is what it means. And the numbers might be a little bit hard to read here, but the x-axis goes from approximately 4,000 on this side to approximately 500 on this side. The y-axis is percent transmittance. So again, if we think back to how the IR worked, when the infrared light was hitting the sample, some of it was being transmitted through the sample and making it to the detector, but some of it was being absorbed by the molecule and not making it to the detector. And so you can think about the y-axis in one of two ways. You can either say how much of the light got transmitted through the sample and made it to the detector, or how much of the light got absorbed by the sample and did not make it to the detector. So you'll often see IR with one of two possible y-axes, percent transmittance or percent absorbance, but by far percent transmittance is the most common standard way of doing infrared. And with percent transmittance, the y-axis then up at the top would be 100% transmittance. Now think about this for a second. If you see a value of 100% transmittance, does that mean that yes, the molecule absorbed light with 100% transmittance, or no, the molecule did not absorb light with 100% transmittance? Transmittance is how much of the light made it to the detector. So if the light is making it to the detector, yes. If it's hitting the detector, then no, it is not being absorbed by the molecule. So that's why our baseline is up here at the top. These are the values that where there was no absorbance, the molecule did not absorb these values, and that's why there's 100% transmittance. 100% of these wavelengths got transmitted through the molecule and did not get absorbed. Where you see a peak coming down, where you see less than 100% transmittance, that's where some of the light got absorbed by the molecule and therefore did not get transmitted to the detector. So the transmittance, so that's why we have our peaks coming down from the baseline. Okay, so when you look at an IR, there are four basic regions that you want to keep in mind. The first region that we draw is right here around 1500. You can draw a bright imaginary line, or even a real line if you want to, at 1500. To the right of 1500, so lower wave numbers, this is what we call the fingerprint region. Every molecule has a unique IR fingerprint. The bending and stretching absorbances, the peaks here in this region, are unique to every molecule. That's very interesting. It makes it very hard for humans to read because the fingerprint region is so different. There's not a whole lot that's characteristic in this region. But the fingerprint region makes it very easy for IR spectra to be cataloged by an electronic database. So you can have an electronic database of IR spectra, and then if you have an unknown IR, you can search it against the database, and it will look for matches, especially in the fingerprint region. And if it finds a good match, then you can be confident that they're the same molecule. So it makes it really good for database searching, but really actually not very good for humans to read. So we will essentially ignore everything in the fingerprint region. Are there things in the fingerprint region? Sure, and different textbooks will have different things to look out for, but for my course, we're not going to really concern ourselves with anything in the fingerprint region. So 1500 and below, we can ignore. I'm going to jump over to the other side. Above around 2500 wave numbers, these are the things bonded to hydrogen. So remember, IR looks at bonds. IR does not look at atoms. IR does not look at molecules. It looks at bonds, which bonds are absorbing infrared light and vibrating, bending, and stretching. So in this region, 2500 and above, this is where we see carbon-hydrogen bonds, oxygen-hydrogen bonds, and nitrogen-hydrogen bonds. So things bonded to hydrogen, these bonds tend to absorb this amount of energy, and so they tend to appear in this region above 2500 wave numbers. We'll get into more specifics a little bit later. The region here between 2000 and 2500 is where we get things doubly bonded to carbon. So carbon doubly bonded to carbon, and carbon that's totally wrong. Triple bond. Carbon triple bonded to carbon, and carbon triple bonded to nitrogen. The region between 2000 and 2500 is the triple bond region, things triply bonded to carbon. It's the region between 1500 and 2000 that we get the double bond region. So carbon's double bonded to other carbons, carbon's double bonded to oxygen, carbon's double bonded to nitrogen. We don't see that too often, but in the event that we do, they would appear in this region as well. So this is our general overview of IR. The molecule is irradiated with IR light. The molecule absorbs some of that IR light, and we see these peaks in the IR extending down from the baseline. And where those peaks show up on the x-axis tells us something about the functional group. In a little bit, we're going to learn about where exactly to look for certain peaks and what that tells us about certain functional groups in the molecule. But this right now is a broad overview of infrared spectroscopy.